Greetings everyone, and welcome back to our online lecture series for CHE 8030 and 4010. In today's lecture, I want to talk about the idea of dimensionality and modeling. And so for the purpose of this class, the dimensionality of a system is the number of spatial variables required to model it. And so up to this point, we've encountered problems that have been one-dimensional, though we may oftentimes find ourselves in a situation where the transport model we initially derive is either two- or three-dimensional. In these cases, we would like to use any opportunity that we have to simplify the model. That's to say, moving from a three-dimensional to a two-dimensional problem, or even better, moving from a two-dimensional to a one-dimensional problem, while still maintaining a desired level of precision. And so a great example problem to highlight the idea or concept of dimensionality and modeling is the cooling fin. And so here I have a schematic of what I am referring to with the cooling fin example. And so in this example, we have steady state heat transfer from an extended surface or a fin to the surrounding air. The base of the fin is maintained at a temperature T0, which exceeds the ambient temperature of the air that is surrounding the fin at T infinity. For simplicity, we will assume that the convective heat transfer coefficient H is constant over the entire exposed surface of the fin. Additionally, we will define an aspect ratio. Here our aspect ratio is gamma, and gamma is equal to the length of the fin divided by the half thickness of the fin. And so for this particular problem, we're going to assume that gamma, or aspect ratio, is much, much greater than 1, i.e. we have a fin that is geometrically thin. Geometrically thin. Right? So our fin's length is much, much larger than the thickness of the fin. Additionally, we are going to make an assumption for this problem that our Biot number, which we will define is HW over K. And again, our Biot number is a ratio of convective to conductive heat transfer. And so for this problem, we are going to make the assumption that our Biot number is very, very small. So, for this problem, we are going to be concerned with the temperature as a function of x and z. We're going to assume that the third dimension, or the y dimension, is large enough that we can neglect any kind of corresponding edge effects. So essentially making this problem two-dimensional at this point. So the first thing we would like to do is choose our appropriate balance. So here we have our energy balance, which for us looks like this. So we have the density, Cp, times the partial of temperature with time, and our convective term, our conductive term, and then our heat generation term. Okay, so that's our general thermal energy balance. Let's make some assumptions so that we can simplify that energy balance. Okay, we will assume we're going to assume a constant density Cp and K. So constant rho, Cp, and thermal conductivity. As mentioned above, or as mentioned earlier, I should say, we are assuming we are operating at steady state. We will assume no convection. And our fin is a solid fin, it's not moving. We will also assume no heat generation. There's nothing that is actually generating heat in our system. All right, Fourier's law. Applies. That's going to be another assumption. And then, of course, as mentioned above, we have two-dimensional heat transfer in the x and z direction. So based on those assumptions, we can simplify our problem. Steady state, that goes away. No convection, that goes away. And we said no heat generation, so that term goes away. And we are simply left with our conduction term is equal to 0. Right, 4 Cartesian coordinates for the x and z direction. Our governing equation therefore becomes second derivative of temperature with respect to x plus the second derivative of our temperature with respect to z. And again, all of that is equal to 0. Okay, next thing we can do is we can list our boundary conditions for the problem. So let's do that. So we will start with our boundary conditions in the z direction. So we are told that the temperature for all x's and z equal to 0, we are holding that at a constant temperature. Right, that is our boundary condition at the base of our film, or excuse me, the base of our fin. And then we have convective heat loss at the tip of our fin. So our convective heat loss, the derivative of temperature with respect to z for all x's and at z equals L is equal to negative h over k. I've moved over my thermal conduction. Temperature at the tip. So this is XL minus T infinity. Again, that is just our convective boundary condition. So we have our temperature gradient is equal to Newton's law of cooling. And again, I have simply moved over my thermal conductivity. Okay, boundary conditions for z direction. Let's do our boundary conditions for the x direction. Right. As implied by the drawing that you see here, we have symmetry in our system. So at x equals 0, our symmetry condition tells us that the flux is equal to 0, which for us we write that as the partial of the temperature with respect to x, again at x equals 0 for all values of z is equal to 0. And then we now need to write our boundary condition at either the top or the bottom of the fin, however you want to look at it. And again, we have convection at that boundary. So the partial of temperature with respect to X at W and all Z's is equal to negative H over K. Our temperature at W and all Z's is minus the ambient air temperature. So again, this is just our convective heat loss boundary condition, where we say that our flux at that surface is equal to Newton's law of cooling. So in reality, we can solve this problem. We have a partial differential equation. We have temperature that's a function of X and Z, and we have our 4 boundary conditions. But before we try to solve this partial differential equation, which we have not been taught yet how to approach those problems, let's think about the case that we're describing here. And so for our case, we are talking about when the Biot number is very small. So when the Biot number is much, much less than 1, or again, you can look at that by saying when the Biot number approaches 0. Let's take a look at that last boundary condition that we wrote. So the partial of temperature with respect to X, W, and Z. Let's go ahead and leave our K here. That is equal to H, T at W and all Z's minus our ambient air temperature. So again, this is just this boundary condition. I'm rewriting that boundary condition. So let's do an order of magnitude analysis on the left-hand side of our equation. And so dt dx, right, my top term. Well, let's do the bottom term first, my denominator. That's a bit simpler. Right, my delta x is on the order of W. Right, again, that is the half thickness of my fin. So the change in thickness in the x direction is going to be on the order of that half thickness. The delta t, the delta t term, if we think about that, our temperature difference is going to be the difference between the temperature at x equals 0 for all z's and the temperature at the surface of the fin, which is at W for all z's. Right, so hopefully we all see where I came up with that from. Again, all I'm doing is an order of magnitude analysis on the left-hand side of my equation. I'm going to take that term, going to plug it back in to the left-hand side of my equation. And so what I end up with is that temperature difference from x equals 0 to x equals W divided by W and that is going to be on the order of H times the temperature at W for all Z's minus my ambient temperature. And I had a K here as well. Don't want to forget about my thermal conductivity. Right, I'm going to rearrange that equation and show that therefore H times W divided by my thermal conductivity is on the order of the temperature difference, right, between x equals 0 and x equals W, divided by the temperature difference between the temperature at the surface of my film minus the ambient air temperature of T infinity. So based on what we defined at the beginning of the problem, we recognize that this term on the left-hand side of the equation is the Biot number. And we told ourselves that for this particular case, the Biot number is much, much less than 1. Therefore, we can write that equation above as such. And so when the Biot number is much, much less than 1, or when the Biot number approaches 0, the variation in temperature inside the film over the x direction is smaller than that between the top surface and the air. So I want to say that again. When the Biot number is very small, we are telling ourselves that the temperature variation in the x direction is much smaller than the temperature variation between the surface of the fin and the ambient air temperature. So in other words, the value of the numerator on the right-hand side of this equation is much smaller than the value, the value of the numerator is much smaller than the value of the denominator. And so we can first ask ourselves, if we write our governing equation, since the numerator is much, much smaller than the denominator, would it be okay to simply cross that term out and leave ourselves with a much simpler equation where the temperature is only a function in the z direction? The answer to that is no. Right? We cannot simply just eliminate that second derivative of temperature with respect to x. Right? What we need to do is replace this term with a term that better represents the heat loss in the x direction. And so as we just stated, the Biot number being much, much less than 1, that means that convection at the fin's surface dominates the resistance to heat transfer in the x direction. So for our x direction, convection dominates. Right? But that second derivative right there comes from our conduction term. And so what we can do here, when we have this very particular case where we have a geometrically thin film and we have the Biot number being much, much less than 1, we can replace the local value of the temperature with the cross-sectional average value of the temperature. And so the cross-sectional average value, so T bar, which is now only going to be a function of z, because again, we're telling ourselves that based on the geometry and the fact that the Biot number is very small, if I start to move away from the center of the fin, the temperature variation between the center of the fin and the surface of the fin is essentially negligible. Right? We can assume a constant temperature in the x direction. So now we have this cross-sectional averaged temperature, T bar, And we can define T bar as 1 divided by W, integral of 0 to W of our temperature, which initially was a function of both the x and the z directions, times dx. Right? This particular action of replacing our conductive term in the x direction with this cross-sectional average temperature is what is known, is what is known as the Finn approximation. And so we can obtain a differential equation that governs T bar by one of two ways. One, we can use this integral to do that. The second way, it may be a bit more straightforward intuitively, is we can perform a shell balance over a control volume of differential thickness. And so in this case, our balance would be over a section of differential length in the z direction, but the full thickness in the x direction. So accounting for conduction in the z direction and heat loss to the air from the top surface, the shell balance that we would obtain is negative kW differential of T bar with respect to z at z. We'll say that's equal to negative kW, the differential of T bar with respect to z at z plus delta z. Right, so that is our conduction term in the z direction. And now we need to account for convective heat loss to the air from the top surface, which we can do with Newton's law of cooling. So H times delta Z. We multiply that by T bar. Which is a function of Z minus T infinity. Right, so again, this is conduction. And this is our heat loss to the air. If we divide through by delta Z and take delta Z in the limit where it approaches 0, we obtain the following differential equation. So second derivative of T bar with respect to Z is equal to H divided by KW, and that multiplied by T bar minus T infinity. And so this becomes our new governing equation for this particular problem. Again, we're talking about a problem where we have a geometrically thin film and we have a Biot number that is much, much less than 1. We would obtain this same differential equation by using the cross-sectional average temperature. So let me at least show you what that looks like. So the first term, 1 over W from 0 to W. And again, we're plugging in our differential equation, which is a function of both x and z. So we'll take the first term, right, the second derivative of temperature with respect to x, this is equal to 1 over w dt dx. And we'll evaluate that from x equals 0 to x equals w. And we would end up with the term negative h wk multiplied by the temperature difference between that cross-sectional average temperature and our ambient temperature. So this is where our term on the right-hand side of the equation comes from. And we can do the exact same thing with our other term in the governing equation. So 1 over w, 0 to w, second derivative of temperature with respect to z, dx. Okay, so here you'll notice that we are taking the derivative with respect to z, but we have our integral with respect to x that allows us to pull out that derivative from our equation. And so what that looks like is we pull that out of our integral, 1 over w, 0 to w, t dx, right, which ultimately looks like that. Right? Because again, this is simply what we have defined up here. And so we end up with a t bar that pops out of that, which is plugged into our second derivative, which we were able to pull out of our integral, again, because the second derivative because the second derivative was with respect to z, and our integral was with respect to x. And so in either case, we end up with the exact same equation, where we end up with the second derivative of t bar with respect to z, and we end up with a heat loss term to the air. So again, we can either do this through a shell balance, or we can do this using this cross-sectional averaged temperature. Okay. So let me box this in so we all know what we're working with here. This, again, is our new governing equation for the problem. Now that we have recast our governing equation in terms of t bar, we need to recast the boundary conditions in terms of t bar. And so let's write those over here. So boundary conditions at z equals 0 and z equals L. So t bar at z equals 0, we know that that is equal to the temperature that we are holding the base of our fin at, which is T naught. And then we know we have convective heat loss at the tip of our fin. And so we say that the derivative of T bar with respect to Z at L is equal to negative H over K multiplied by T bar at L minus the ambient temperature, which is T infinity. So we now have our new governing equation and the accompanying boundary conditions that come with that governing equation. The next thing we're going to do is we are going to define two dimensionless variables, one for the length, and one for the temperature. So our dimensionless variables that we can define, we'll define zeta. That's a horrible zeta. I'm just going to go with it. That zeta. Here, zeta, I'm going to define as z divided by w. And so for these type of problems, when we have a geometrically thin object, the cross-sectional dimension, which for us is w, is often more important dynamically than its length. Meaning here, more often than not, the dimension of w is more important than the length of our fin. What we're going to find out is, in fact, w or l, whichever one we would have chosen to put here, neither one of those is going to be correct, right? So we're going to need to rescale our problem, but just based on, sort of practice with this, knowing that more often than not the cross-sectional dimension is more important than its length, I'm going to go ahead and initially non-dimensionalize z using w. My temperature variable I will define as theta. And here theta is going to be equal to T bar minus T infinity divided by temperature at the base minus T infinity. This is the highest temperature we can have. This is the lowest temperature we can have. And so again, we would like to non-dimensionalize our temperature difference by the largest temperature difference that we could have in our problem. And that's why we choose T naught minus T infinity for the denominator. Let's transform our governing equation and boundary conditions using these new dimensionless variables. When we do that, we end up with the following equation. So that is our governing equation and our boundary conditions that come with that. Theta at 0 is equal to 1. So when T bar is equal to T naught. And then we have our convection at the tip of the fin. So d theta, d zeta. That is going to be equal to negative Biot number theta at gamma. And again, keeping in mind here that gamma for us is L over W. Okay. So, if we look at our governing equation and our boundary condition, we notice that for the case where the Biot number is much, much less than 1, our problem is not scaled properly. What do I mean by that? Okay, so let's look at our governing equation. When the Biot number is much, much less than 1, or the Biot number approaches 0, right, our governing equation tells us that the second derivative is equal to 0. And the implication of that is that the temperature profile inside our fin is linear. Second derivative equal to 0, I integrate that twice, I end up with the equation for a line. Right, so when the Biot number is small, our governing equation is telling us that the temperature profile should be linear. However, if I look at my second boundary condition, when the Biot number is really small or approaching 0, I am told that the derivative of theta with respect to zeta is equal to 0. And so the implication of that is that the temperature profile has some curvature to it, where the temperature gradient vanishes at the tip of the film. I keep saying film, at the tip of the fin. So I want to say that again, just to be clear. When the Biot number is very small, we see from our governing equation that we should get a linear temperature profile inside our fin. However, when the Biot number is very small, we are told that the derivative of that temperature is 0, right? Implying that there is some curvature to the temperature profile inside our fin. And so what that tells us is that we have not properly scaled our problem because we have a conflict between what the governing equation is telling us and what the boundary condition is telling us, right? And so this contradiction that we see here is caused by the fact that we have this very small value of the Biot number. And if we remember from the last lecture, when we ran into problems where we had a parameter that was causing us an issue with scaling in our problem, what we did was perform a coordinate transformation so that we could remove that term from our governing equation, right? Therefore, removing this contradiction that we see. So this is an analogous problem to the diffusion reaction example that we did in the last lecture. So I will define a new dynamic length scale of capital Z. And I'm not going to go through the math because it's exactly the same. We find out that, right, that exponential A that's a constant ends up being a half. And that is multiplied by zeta. Right, for us, zeta is Z over W, so I'm going to go ahead and plug that in. Our Biot number is HW over K. And so what we end up with is the following equation for capital Z is H divided by WK to the 1/2 times Z. And so what this indicates is that the proper length scale, the proper characteristic length scale for this particular problem, when the Biot number is very small, is actually W times K divided by H to the 1/2 power. Right? So this is actually our correct characteristic length scale. Right? So that we end up with a problem where we don't have this contradiction between the governing equation and the boundary conditions. Therefore, we can redefine our boundary condition. So our boundary condition at the tip, so d theta, we have a new variable, capital Z. Right, at lambda, and I'll tell you what lambda is in a second, is equal to the negative Biot number to the 1/2 times theta at lambda. Where lambda is equal to H divided by WK 1/2 times L. So essentially, lambda is just a new variable that we're using to define when z is equal to L, or when we are at the tip of our fin. Okay, so we can use this new variable. We can recast our governing equation so that we can remove this problem parameter here, our Biot number. When we do that, we end up with the following governing equation and following boundary conditions. That becomes our new governing equation, and our accompanying boundary conditions are theta at 0 is equal to 1. And again, very small Biot number, we end up with our convection term and again, lambda is simply when z equals L. That is equal to 0. So now that we have properly rescaled our problem, we have no contradictions between our boundary condition and the governing equation. We feel good about how we've scaled this problem. The solution to this differential equation takes the following form. So theta as a function of capital Z is equal to the hyperbolic cosine of Z minus the hyperbolic tangent at at lambda times the hyperbolic sine of capital Z. So again, that is the solution to our governing equation, applying those two boundary conditions. So if we were asked to come up with the non-dimensional temperature profile inside that fin for the case where we have a geometrically thin fin and we have a Biot number that is much, much smaller than 1, this is the solution to that governing equation. Right? That is our dimensionless temperature profile inside the fin. And so when we have a short fin, i.e. lambda is much, much less than 1, we see that we have an isothermal scenario at the base of the fin. That is, theta is equal to 1. And when we have the scenario of a long fin, or lambda is much, much greater than 1, what we see is that the solution to that equation, it becomes theta approaches e to the negative capital Z, which is a analogous solution to what we saw in the diffusion reaction problem before. And so for very long fins, or fins that are geometrically thin, right, this becomes a good approximation to describe the temperature profile inside that fin so that the temperature reaches the ambient temperature well before the tip of the fin. So hopefully that example will help you work through and rationalize how to solve problem 1 on the homework. Please watch the video multiple times if you need to. And of course, if you have any questions or concerns about anything that I've gone over in the example problem, please feel free to email me, or we can discuss those questions in class on Tuesday.